This is the screencast for section 6.5, example 6, logistic growth models, and we're going to be using our calculator here in a minute. But right now, here's some information that may have made our lives easier in example 5, but you know, math teachers, we got to make you go the long way before we give you the shortcut. So if you have a differential equation for logistic growth, the original equation, usually representing population, is m over, and we already knew that that would be our limit to growth, or our maximum carrying capacity, over 1 plus a is a constant we have to solve for, e to the negative. Now here's where the cool part is. That coefficient of t is just m times k. And that's going to come in handy here in example 6, but let's first take a look back at example 5 and show you why it's just m times k. So here in example 5, we did all this messy work, but here's our t value as we're trying to solve for the population model, and in front of t is 0.0003, the k value, see right up here, the k value, and then we're multiplying both sides by 1,000, 1,000 is the m value, so there you go, k times m. We do the same thing here in the Now Try problem number 29. Here's your k value, 0.0002, k value, times 1200, the m value. So that coefficient of t is just m times k. So now in example 6, we're going to see how that comes in handy. Table 6.6 shows the population of Aurora, Colorado for selected years between 1950 and 2003. Use logistic regression to find the logistic curve to model the data and superimpose it on a scatter plot of population against years after 1950. So the years after 1950, I put in L1, and then population I put into L2. I did a logistic regression and got this, plotted that into Y1 along with the data points, and there is my logistic growth equation. Now, based on the regression equation, what will the Aurora population approach in the long run? So in other words, what's the maximum carrying capacity or limit to growth? Well, that would be, let's see, 316,440.71 people. The calculator calls that a C value, and the C value is right here. Part C. Based on the regression equation, when will the population of Aurora first exceed 300,000 people? Well, 300,000 people is getting really close to my limit to growth, so I actually extended out the X max so that I'd be able to see that a little bit easier. And then I found the intersection, and I got that that would be at about 59.13 years. So that would be years after 1950, so 2009. Now here's the cool part. Write a logistic differential equation in the form dp dt equals k times p, whatever you got that models the growth of the Aurora data in table 6.6. Okay, so I only have the population model. Well, I don't have to take the derivative of that now because I know how this equation relates to this equation in terms of m and k, the two constants I have to solve for. So here's my population model, which means that m is your 316,440.71, which also means that m times k is the coefficient of t, negative 1.03, but really this whole big long decimal. So if I divide both sides, or plug in my value for m and then divide both sides by m, I get that k equals 3.24 times 10 to the negative 7. So now I can put that in to my differential equation format, where k is my 3.24 times 10 to the negative 7, and m is 316,440.71. Much shorter than taking the derivative. The Now Try problem number 37 explores the same context. Table 6.7 shows the population of Laredo, Texas for selected years between 1950 and 2003. So we're going to use logistic regression to find a curve to model the data and superimpose it on a scatter plot of population against years after 1950. So population went into L1 again, population went into L2, did a logistic growth regression, and found that, put it into Y1, and then obviously turned on plot 1, and then superimposed those. Now part B, based on the regression equation, what number will the Laredo population approach in the long run? So what's the maximum carrying capacity or limit to growth? Well, that would be my C value from my calculator, 232,739.87 people. Now, based on the regression equation, when will the Laredo population first exceed 225,000 people? So again, I changed my X max here to something that would extend beyond my natural window around my data, just because that 225,000 is getting very close to my maximum, so I need to see pretty far out to the right on this situation. And then I put into Y2 225,000, found the intersection, and I got that was about 59.73 years. Part D, write a logistic differential equation in the form dp dt equals that form that models the growth of the Laredo data in table 6.7. Well, the population model from the calculator is this, which means that M is the numerator, and then it also means that M times K is the coefficient of T, 0.0 or 0.101. So if I plug in my M value and divide both sides, I would get that K is 4.352 times 10 to the negative 7th, and now I'd be able to create my differential equation for logistics.